Good morning. Testing, testing. This is Marnie, LaNoue, Chief Scientist of Evidential Consulting, and this is a two-part lecture on exploratory factor analysis. In part one, we will introduce some of the basic concepts of the method, and in part two, we'll look at a few more of the technical details. Factor analysis, generally speaking, is a data reduction or dimension reduction approach when you have many within-person variables. Those variables are generally expected to be correlated with one another because they are coming from the same data source. And the goal is to reduce a large number of measured variables down to a smaller set. So, for example, if at the individual level you had 40 variables from an electronic health record that you wanted to use to predict an outcome like likelihood of hospitalization in the next 18 months, you could use a factor analytic approach to try to reduce the complexity or number of those 40 variables down to a smaller number. Or you want to reduce some variables down to maximize their predictive value. So, for example, using like a comorbidity score like the Charleston or the LACE, and you may want to or not want to use that to predict some future outcome variable. In the case of a battery of questions that might be written in a measured development context, if you want to measure one single measure and some underlying within-person phenomenon like burnout, 50 might be too many questions, and you could use a factor analytic technique to do some things like think through whether those are the appropriate questions, the right questions, too many, too few. Or, for example, a battery of aptitude tests is really where this technique began, and that's a common application. We'll talk about that in just a sec. So generally speaking, when you hear the term factor analysis or exploratory factor analysis, what people are talking about is a data reduction technique or dimension reduction approach that groups variables when those variables are at the individual level, and there are many of them, together into sets that are meaningful. And we define meaningfulness as the degree of interrelationship among those variables. Meaningfulness, or the way variables hang together, can also be thought about in common sense terms or previous literature or clinical interpretability of a group of variables. And there are ways to group variables together just sort of conceptually like that are not an analytic or a statistical approach. But when you hear the term EFA or just factor analysis generally, what people mean is that the original set of variables are going to be reduced down into sets where those sets are linear combinations of the original variables. And scores can then be produced on the new variables that at the individual level, so that they could be used, as we said, in prediction models or descriptive models, and where those scores would then be new scores on the reduced set of factors that arise from the factor analysis. And factor analysis in general can be thought of as belonging to two different paradigms, or two different sort of approaches to measurement, or two different measurement models that are quite different and have two different goals. We are going to approach this lecture, and as behavioral scientists in general, probably the more common approach is one that's shown on the bottom of the slide, which is the assumption that the interrelationships among the person-level variables exist because the variables share a common cause. And that's generally what's called the common factor model, or a true factor analysis, if you're thinking about it analytically. The other sort of worldview or sort of paradigmatic approach to factor analysis is entirely as a dimension reduction technique, where you are eliminating multicollinearity, which is highly correlated variables, for example, that are going into a regression together are multicollinear and should not be entered simultaneously into a regression model, or you are sort of parsing out when you have too much information that's useful, so too many variables altogether for predictors in a regression, or a correlation matrix that's too large to be interpreted. And the analytic technique used there principally is what's called principal components analysis, or PCA. They are not the same thing at all. They rest on different assumptions. They analytically are implemented differently. And so the first point, I guess, to think about as a learner is when you're reading an article to really look carefully in the methods section and see if what has been done is a principal components analysis or if what has been done is a factor analysis. And it's a little tricky to figure out what's what sometimes. Often just called a true factor analysis or just factor analysis, but many times the words factor analysis will appear somewhere in a paper, but then if you read more carefully, you'll see that what they actually did was a PCA, a principal components analysis. The conceptual distinction between those two approaches is, simply put, either the idea that you're doing variable reduction or dimension reduction to eliminate multicollinearity, and that the way you're doing that is by using your original variables, which are shown on the right with the V's, V1, V2, down through V sub K, and putting them together into a linear combination to create a component. You're not doing it. That's what the statistical machinery is doing. But this should look familiar in terms of the directionality of the errors, that the original variables are linearly combined to create a component. So look for the word component. Generally is a clue that has been done as a principal components analysis. And the equation is a single linear equation that says the component is a function of variable 1 times its weight, variable 2 times its weight. Those weights are empirically derived, and so on down through variable sub k. This is a single component model, obviously. And so because of the direction of the arrows all pointing into the component, that tells you that in fact what's happening is the variables are being combined in some way to produce the component. The second worldview, which we said is the one that corresponds most closely to what we do in the social and behavioral sciences, the true factor analysis, or you'll hear me say lots of different terms here, common factor model, true factor analysis, is that the interrelationships among the observed variables exist because the variables share a common cause. The reason that people respond the way they do with, at the individual level and across your whole sample, the reason that responses look like they do on the measured or manifest variables, which we often call indicators, is because a single common cause is driving those responses. And that's visually depicted here with the factor and its arrows pointing out to the manifest or observed variables. So what we're saying here is a single underlying dimension or single common cause causes there to be the scores that are observed in the data. And that's also demonstrated on the left-hand side of the screen, where variable 1 is a function of the underlying factor, the amount of that underlying factor that the individual has, plus error down through each individual item. So you can see on the right-hand side in the visual depiction are shown the error terms. And the reason we switched the equation around is to show that we're not saying that the factor now is a function of the underlying variable. We're saying the variable is a function of the underlying factor. And when the error term is present, we are saying observed scores on the variables are comprised of nothing but underlying measure and whatever that underlying common cause is. And that's also demonstrated on the left-hand side of the screen, where variable 1 is a function of the underlying factor, the amount of that underlying factor that the individual has, plus error down through each individual item. So you can see on the right-hand side in the visual depiction are shown the error terms. And the reason we switched the equation around is to show that we're not saying that the factor now is a function of the underlying variable. We're saying the variable is a function of the underlying factor. And when the error term is present, we are saying observed scores on the variables are comprised of nothing but underlying measure and whatever that underlying common cause is, plus the individual level errors. So again, here is the overview with a little more detail. We have these two, what I'm calling here, worldviews or conceptual approaches to factoring, which are number two, the one we're going to focus on, where the goal is to uncover the underlying data generating mechanism. So does some underlying latent or set of latent variables explain the associations or patterns of correlation I see among my measured variables? And worldview one, the principal components the goal is to reduce the number of variables. And the question we're asking is, can I reduce these variables down into a more parsimonious set? And that's principal components. Principal components is common in healthcare or medical settings when the goal is to, for example, reduce, some large number of variables from a data source that's not an individual's. Well, it's still an individual level data source, but for example, I could pull 40, 60, 80, 100 variables from someone's electronic health record, right? Which is a very sort of machine learning kind of algorithmic approach to prediction. And I'm just asking, can I reduce the number of variables I have down to a more parsimonious and useful set? That's worldview one, the principal components world. Worldview two is, again, can I explain the patterning that I see in the associations, the correlations among these measured, observed items, so what we're generally talking about here, right, is like a scale where the items or the associations among the observed variables are questions on a measure. And that corresponds to what we've been talking about in terms of measurement science and identifying measurands. What is the underlying measurand? What is the thing that exists within people that I'm trying to uncover here? And if I have 25 or 30 questions that I use to try to tap that underlying thing, I'm going in with the assumption that the reason people at the individual level and across the sample, the reason people respond the way they do is because of some underlying latent variable that's within person. So contextually, this grew out of the work of some seminal early psychologists like Spearman and Pearson, who developed correlation coefficients to measure associations between pairs of variables. They did overlap very much so in terms of the times that they lived. They pioneered the use of factor analysis and PCA for data reduction and identification of underlying constructs. Of course, Pearson, when you think about a correlation, what generally you're thinking of is a Pearson correlation. Spearman developed the rank correlation or the Spearman correlation, but it was Spearman who proposed the concept that if you thought about administration of aptitude tests, this really was the beginning of the early intelligence work. If you administered a battery of aptitude tests to a person and then across an entire sample of people, and the bullets that are shown on this slide represent a subset of the kinds of tests that are given even today in what we call the Wechsler Adult Intelligence Scale, or the WAIS. So, for example, produce the names of as many fruits as you can. You give someone a minute to do that. Memorize a list of words and then repeat it back to me. Do things like add, subtract, divide, mathematical operations. Put these pegs into these holes as quickly as you can. So there's sort of a motor reasoning or a motor skill test. Same with putting a puzzle together. Things like what are called the matrices, where you have to figure out which picture comes next in some sequence. Spearman's insight was there's one underlying ability that produces all of the patterns of responses that you see on scores. And in this case, the pattern of responses would just be those who score high on one tend to score high on all of them. Those who score low on one tend to score low on all of them, because one underlying ability was producing, right? One underlying within person latent variable was responsible for how people score on those tests. So to recap, generally, what you might want to do is uncover some within person underlying data generating mechanism using what's called a common factor analysis or true factor analysis. rather than strictly doing dimension reduction. And also conceptually, as a starting point for us in this discussion is we're going to do that by trying to maximize or produce factors or uncover existing factors that maximize the variance explained across all of the questions or items that you have. And we want to do that by maximizing the shared variance. In principal components analysis, what is being done is that the total variance is being maximized. It's an approach that takes all of the variability in the entire data set and tries to maximally extract components which account for observed variability. Whereas in factor analysis, we're trying to maximize the variance that's shared among the individual indicators or items. And that is quite a big difference, actually. So again, if you think about the common factor model as saying that the interrelationships among the observed variables exist because the variables share a common cause, then we're saying the only thing present in the observed variables, the only source of responding in the observed variables, comes from the common underlying factor or dimension. Anything that isn't attributable to the underlying factor has to be considered to be error variance. And so in the common factor or true factor analytic approach, we don't want to model the error variance, right? We just want to model that variance that we see as arising from the underlying factor. And that's the chief mathematical distinction among the techniques. Instead of trying to model all of the variability in the data, we're just going to model that variability which we believe is attributable to that underlying factor. So to sum up that overview, in principal components analysis, simplicity or reduction is the goal, while in factor analysis, true factor analysis, discovery is the goal. We're trying to discover how much of the variability in our observed variables can be explained by a single underlying dimension or perhaps a couple of underlying dimensions. And we're going to use the interpretability of the data, the interpretability of the results to guide us to do that. Whereas in the principal components analysis, generally what's being done is being done for predictive purposes. And so, and success might be the predictive ability of the components that are derived from the analysis. In factor analysis, we are assuming that the data generating process is within person, whereas in principal components analysis, the data generating process can be anywhere. It could be within person or outside of them, or a mixture of both. And in factor analysis, we are assuming that the latent variables underlying responding are reflexive variables. So that the individual person, the individual latent variable itself is causing scores on the manifest or observed variables. Whereas in principal components analysis, the observed variables are being used to form the underlying composite. Principal components analysis is generally easier to conduct and interpret, I think, which explains why it's a more common analytic approach, even when it's an inappropriate model. Factor analysis is more difficult to conduct and interpret. But again, if your thinking as the scientist or the analyst is that there is a within-person phenomenon causing scores on the observed variables, then a true factor analysis or a common factor approach is the more appropriate approach. That gets you to look at these questions. This is a subset of questions from an actual measured, published measure. And I'm going to put us on break for like 2 minutes while you sit and sort of think through these questions. If I ask you what I'm going to ask you is, do these questions look like they could reasonably conform to a common factor model? Or does a common factor model adequately represent a source of responding, where the common factor model says there's some underlying latent variable, perhaps 2 or 3 latent variables, which explain how people respond to these questions. These are Likert scaled questions from 1 to 5, strongly disagree to strongly agree. And then beyond that, do any of these questions look like they go together? And when I say go together, simply conceptually, like is there one or two or three, maybe four groups here that make sense as underlying dimensions? So the first question you're asking yourself is, do these look like a reasonable source of variability in responses? Could be a within person latent variable. And then if so, how many of those things might exist? Just take a look at it and ask yourself, if I gave you a stack of 3x5 note cards with each of these sentences printed on a single card and said, put these in piles that make sense to you, how many piles would you have? Just take a look at it and we'll be back in 1 second. So I've done this exercise many times with different individuals. So I've done this exercise many times with different individuals doing the sorting task or groups of people doing the sorting task together. And generally, people come up with 2 or potentially 3 separate piles of ideas here. If you've heard me speak about the group concept mapping technique, this is very similar to what would be done in the sorting phase of group concept mapping. And really what we're trying to emphasize with this exercise is, in a factor analysis, when you're uncovering or working to uncover underlying dimensions, underlying latent variables within person data generators, we assume that patterns of responses on observed variables are there because the underlying data generating mechanism produces them, the within person latent variable. And these questions, I think, generally should feel that way, right? Like if this is some phenomenon, some concept that exists within people and gives rise to scores. Maybe you came up with a couple of piles. One of them might be something with like quality of care or trust in the medical system, right? And one of which might be an individual's confidence or efficacy in managing their symptoms. So we are going to mathematically factor analyze these in a sec. And what we expect to happen is that the analytic approach will produce the same thing that an individual sort of conceptually thinking about this would produce. And that's the beauty of factor analysis, and kind of the miracle of factor analysis is you can dump a set of items in, and then the sets or the factors that arise from the analysis conceptually make sense, right? Because as we said in the beginning, it makes sense, it's interpretable, it's meaningful, or the sets of the factors that come out of the analysis make conceptual sense as falling the way they do or hanging together the way they do, because there's a common cause of responding that exists within the person. Okay, so as I said before, the 2 factoring approaches are based in taking the observed variability and the patterns of correlations or associations among the observed variability and modeling it. In the common factor model, only that variability at the item level that can be assumed to be due to the underlying latent variable that is called shared variance across the items is what we're going to model, because we're assuming that if a single within person data generator is accounting for the patterns of responding, then the only variability that matters is that variability which is shared across the variables. Anything else has to be assumed to be error variability, and we don't want to model that, because the items, the equation that describes the items is F, i.e. the factor, equals the observed score on an observed variable, or the score on an observed variable, plus error. We don't want to model that error term because that's sources of responding that cannot be accounted for by the underlying factor. And in a PCA, an attempt is made to extract or model all of the variability, because even the error variability may contain some systematic variability that could be used for prediction. This slide just sort of depicts that. If you think about the total variance of an observed variable, the total variability of a single variable if you have let's say N equals 150 people responding to the questions that you just looked at, and the first question is, I am not sure if my symptoms are signs of a life-threatening disorder, and you get 150 people to respond to that question, and it's scaled 1 to 5 for the response option, then you're going to have some mean on that variable, and you're going to also have some variance, right? Both a standard deviation and a variance for the item. And what we're saying here very, very explicitly is the variance, the total variance in that item is comprised of common variance, which is that which is shared with other variables, error variance, which is the stuff we don't care about, and specific variance, which is variance that's not shared with the other variables but is not error. All we're going to model in the principal axis factoring approach, or that was the true factor model or the common factor model, is the common variance or shared variance. The PCA tries to model all 3 of these sources of variability. Again, the reason for that is because if we're assuming an underlying latent variable in the factor analytic approach, what we're saying is observed scores can be comprised of nothing but the underlying true score and error. And our job is just to model the all of the unique variance of that item, which is an error. Okay. So another way of articulating that idea is the entire set of variables, the entire set of measured, observed items or variables has a specific structure. That structure can be thought of as the correlations among them. So here's a correlation matrix for a few of those items. It's just the correlations among every pair of items or questions in the set. And it has also a variance covariance structure. So the variance covariance structure is just another re-expression sort of the correlation matrix. So we're going to keep this conversation at the level of the correlation matrix. But in any case, your observed items, indicators, have some structure. We're going to represent that structure by looking at the correlation matrix of the original variables. And what we're going to try to do is, with our model, is to reproduce the correlation matrix on the basis of the factors that we extract from the model. And of course, we're not going to entirely reproduce it, but the extent to which we can reproduce it tells us something about how well our model fits. How well our model fits answers the question, is the patterning of responses here best explained by assuming some underlying within-person data generator that perhaps is unidimensional, perhaps is bidimensional, something like that. So here's the correlation matrix. So hopefully it makes sense that all of these items are intercorrelated, some of them more than others. So for example, question 2 and question 5, if you look at the intersection of those in this matrix, you'll see that the correlation is 0.43. In a large sample, a correlation of 0.43 between 2 questions is pretty high. Some of them, though, like question 2 and question 11, so question 2 says, I am afraid that my symptoms will get worse. And question 11 is, I am unsure whether the doctors who treat me have adequate medical knowledge. Those 2 are correlated. In this sample, they are not statistically significantly correlated, but that's probably driven largely by sample size. But in any case, as you can see, the correlations are, as you would expect, positive with a pretty large magnitude. And what we're going to do is try to extract factors from these questions that can reproduce the original correlation matrix between all pairs of variables present in the data. Okay, so that's the overview. We're going to walk through the steps of an exploratory factor analysis using a true factor analytic model. And we've already done the first 2 because the number 1 is sort of decide on which approach you want to use with your data, factor analysis versus principal components. And then in terms of doing the analysis, the next thing is to perform the extraction, the factor extraction or the component extraction. And that extraction is nothing more than a button click that represents the choice that you made in number 1. So you get into the data and you say, give me use a extraction approach that's based in a common factor model, or use an extraction approach that's based in a principal components model. So we've already sort of done those things before we even sat down in front of our data. Before we do that, let's look at factorability. So factorability is the extent to which the data are going to yield themselves to a factor model, and then we'll look through the other steps next. Factorability answers the question, is this a data set suitable for finding underlying factors? And that's because, as we've been saying, an exploratory factor analytic model using a principal axis approach or a common factor model assumes a common cause model. Again, that the variables share common variance, that the pattern of correlations among those variables is explicable because they are manifestations or they are effect indicators of some common cause latent variable. So if the variables don't share enough variance, then there's no meaningful structure to find. And there's a couple of tests of factorability shown here, both of which can be gotten out of SPSS or both of which can be gotten out of R, whatever approach you use for the factor analysis. So they just answer the question of, do these variables have enough total variability and enough shared variability for a factor analysis to make sense? So then the next step we would do is look at what are called the communalities. The communalities are a representation of the proportion of variance in each variable that can be explained by underlying factors or underlying continuous latent variables. So we want that to be high, reasonably high. We're going to look at the communality for each variable, and that is going to tell us the factorable, sort of the factorable variance, because in the common factor model, again, we're only going to try to factor or model the shared variance or the common variance among the items, and we're going to exclude all of that other stuff. And so this is sort of a step 2 in the terms of asking the question, is there enough shared variability here to be modeled? And your output is going to show you 2 sets of communalities. The first set is called the initial communality, and the second is called the extraction communality. So the communalities do not determine, they don't really tell you a lot of information about your factor model, but they're important because they tell you how well each variable is represented by the factor solution. So the starting or initial communality is how much shared variability is there for that specific item. Communalities are at the item level. And then that's before things are factored. And then after factoring, you get an extraction communality, which is the proportion of each variable's common variance that was explained by the retained factors. So you want the communalities to be high. In principal axis factoring, which is what we're now calling our common factor approach, so not PCA, but a common factor or principal axis approach. And I use that expression only because that's what SPSS calls it. The principal axis factoring approach is synonymous with the common factor model, at least in SPSS. And that's just historical precedent. It didn't need to be called that, but that happens to be what it's called. What happens, as I was saying first, is each individual item is examined for its squared multiple correlation with all the other items. And then after extraction or after the factor analysis is done, you're given the result, and that result says the proportion of that variable's common variance explained by the retained factors. So the initial or the starting communalities are actually smaller than the extraction communalities because the initial communality represents that variable's correlation with every other variable in the data set, the squared multiple R squared. It's the R squared for that variable's relationship with all the other variables in the data set. And then after the factor model is produced, the extraction communality shows how much of each variable, individual variable's common variance was explained by the retained factors. It's just a note because in a principal components analysis, the reverse is true. The initial communality is very high because it represents all of the variance that is being modeled. And then the extraction communality drops down because it's telling you, here's how much of the total variability I was able to squeeze out of this model. So the pattern of initial and extraction communalities is opposite. So the rest of these slides are going to show some output from SPSS using the principal axis factoring approach to the data that you did your conceptual sorting with, but not just those questions. Those questions represent a subset of items that themselves that we're going to use here in this factor analysis represent a subset of the total items. The reference for this project is at the end of the slide deck. This is a scale that I published in 2018, I think 2019. So this is some of this output is based on these exact questions, and hopefully that makes sense to you. And this isn't just another re-expression or examination of the idea of looking at the communalities and what they represent. Communalities are at the item level. They're not at the factor level, and they just tell you, how well the model was able to account for the variance of each item. So if you're developing a measure and you have, let's say, a candidate pool of questions, the communalities could be very informative in terms of thinking about which items should I retain for my measure, which items are no good. In the best case scenario for measure development, you would have a big candidate pool of items, and this would be a first step in thinking about items which are functioning well and items which are not, and then you might use that to revise your measure. If you're using a published measure and it's too late for revision, then the communalities are not necessarily that important, but they might be interesting to look at just in terms of thinking about item functioning to compare with other studies that have used the same measure. You can see that some of these are very, very high. Look at question 10, right? The extraction communality there is 0.635, which means 63.5% of the variability in that specific item is accounted for by my factor model. That's a good high functioning factor model. But the first one, the lowest one, yeah, it's 26.4% of the variability in that item is accounted for by the factor model. Okay, so the next thing that we're going to think through is we've dumped all of our individual within person measured variables into the machinery of exploratory factor analysis. We've looked at the total variability, the shared variability of the items, or that we're going to use to extract our factors. We've looked at the communalities. Now we're going to be presented with the question of, how many underlying factors are likely in this data. So we have to decide on that ourselves. And let's think about how we might do that. You're going to be given, so let's just sort of separate this out to say the first conceptual and statistical checks that we did were at the item level. We're now going to start looking at things at the factor level. How many factors underlie these data? So at the factor level, we're going to look at what's called an eigenvalue, which is the total amount of variability, the total amount of the shared variability in the items explained by each factor. And there are a lot of different ways to decide if a factor is a good factor or not. Conventionally, everything has been done with what's called the Kaiser rule or the Kaiser criterion, which is that you should retain factors that have an eigenvalue greater than 1. But you should combine that potentially with a visual examination that we're going to look at in the next slide, or a parallel analysis is really nice. Unfortunately, you cannot implement a parallel analysis in SPSS, so I leave it out of this presentation. In addition to examination of the eigenvalues, what's called a scree plot, which is what is shown here on screen, has been historically what people use to make that decision. And the scree plot is nothing more than a visualization of which factors do have eigenvalues greater than 1. So you can see that there's a first factor that's to the far left of the x-axis. It's a very high eigenvalue, showing that that first factor accounted for a lot of the shared variability. The second factor has an eigenvalue over 1, and it's actually a little over 2. And then the third factor still has an eigenvalue greater than 1. So factor 1 explains a large amount of the variability with the of that factor with respect to the underlying items. Factor 2 is still working well. Factor 3 is still working well. What we're looking for generally in the scree plot is where the line starts to level out. And you can see that that's at factor 4, right? Even though factor 4 has an eigenvalue less than 1, you might still consider it in your factor solution because that's really where the scree plot starts to, become a horizontal line. I haven't said this yet. I'm going to say it now. We're going to make a big deal out of this at the end. Factor analysis is an exploratory technique. It's called exploratory factor analysis. There's a lot of subjective decision making that has to be done at the analyst level in terms of producing a final solution. Factor analysis is a subjective, data-driven process, data-driven and then also analyst-driven. Lots of analytic decisions have to be made as you go. Probably the most important analytic decision that has to be made is how many factors should you retain? You can use the Kaiser rule, the K1, right? Any factor with an eigenvalue greater than 1. There's a number of other criteria that people have proposed, right? Like you're retaining the number of factors that explain some predetermined set of variability, achieving simple structure, which we'll look at in a second. But the most important thing is probably the interpretability of the factors. So think back to the sorting task that you did. You looked at those questions yourself and said, which of these feel right? Which of these are meaningful and interpretable together as a set? And in the end, it's going to come down to the decision made by the analyst about interpretability. That probably should drive, I should bold that and put it in red. That's really what drives the final solution. The quote at the bottom just sort of says that again, that resolving the number of factors issue is more art than science. Exploratory factor analysis is an exploratory technique. It's not an inferential technique. There are no p-values. And the final decision should be the interpretability of the resulting factors. We'll look at that in a second. Simple structure is an unachievable goal, but still worth noting here. This comes, again, historically out of the roots of factor analysis. Simple structure is that there's going to be a matrix, and we'll see it in just a sec, that shows each factor in the column and each item in the row, and it's going to show us the degree of relationship between the items and the factors. And so, again, what we're doing is just like in your own conceptual sorting exercise, so we're looking for groups of items or questions from indicators, right, observed variables that comprise that factor. And so what we want to see is that each observed variable has a high correlation with only one of the factors, right? That's what's in each row should contain at least one value near or near 0. And that the columns should have several entries at the item or observed variable level with values near or close to 0. So hopefully that makes sense. We're going to look at that in terms of our results in a second, but I just wanted to let that sink in first. Okay, so now here comes the question of rotation. Rotation is common in exploratory factor analysis when using the common factor model. It should be less common in a PCA, in a principal components analysis. Rotation is a tricky technique that rests on altering the factor structure a little bit to make the resulting factors more interpretable without altering the underlying data. So let's take a look at what that means. Think of the factors themselves that are extracted from your model as axes in a multidimensional space. And it's easiest to think about this, for example, if we had a model that had extracted 2 factors, which is what we're going to look at, like this. So those 2 x, y axes represent 2 underlying factors. And the points are the questions or the items or the measures that went into it. So you can see the points are sort of just laying all around, right? And here's a 2-factor solution. So when we rotate, we're not moving the dots. The dots stay where they are because with respect to each other, right, we can't alter the underlying structure of the data. So the dots are not going to move because they are where they are. Instead, what we're going to do is rotate the XY axis, right? We're going to rotate the factor axes around those points until we get a better fit. The rotation can't change how much of the total variability is explained in the model or how much of the item common variance has been extracted in the factor model because the data, again, they are what they are, right? They share the amount of common variance. The items share the amount of common variance that they do. We can't do anything to change that. We're just going to rotate the factor axes around a little bit to make them more interpretable. So let's take a look at that. These data are represented two-factor solutions. So factor one is the vertical up-down line, and factor two is the horizontal line. The values that lie on those axes can be considered arbitrary. This is, let's say, in a standardized score space, right? So some of the values above the line on the vertical or to the right of the intersection on the horizontal line, those are values that have a positive standardized value, and the other ones have negative standardized values, but it doesn't really mean a lot. It's not important for you as the analyst to know what those values are. This is just a way of representing these data in space. We use the word orthogonal to represent uncorrelated factors. So this visualization is showing us an unrotated or orthogonal solution. And when I say solution, what I'm saying is these are the factors that we have extracted, and they are uncorrelated or orthogonal with respect to each other, and unrotated in that no rotation has been done yet. So this would be a typical first extraction, and actually also very typically the final extraction in a principal components analysis. But for a factor analysis, this might be the first extraction that's done, just to get a sense of what's going on. And then, as I said, we can move forward and start rotating the solution, which is just the rotation of those two axes in space, to make the patterning of associations among the measured items more meaningful. So let's take a look at some rotations. So here's a rotated solution. You'll see that the axes are still completely orthogonal. They're still at right angles to each other, but they've been rotated. None of those dots have moved. None of the dots have moved at all. In fact, you can see that, right? The dots have not moved. Just the orientation of the factor axis has moved. But I think it's pretty easy to see in this case that now we've got a cleaner solution somehow. The dots are now more closely related to the factor, i.e. the dots are now closer to either one line or the other and less related to the other line with nothing more than just a simple rotation of the factor axes. So rotation is often done to make the resulting factor solution more interpretable, more meaningful. It's easier to understand the patterning of the data. Nothing else has been done but a rotation of the factor axes. This is still an orthogonal rotation. Orthogonal meaning the two factors here are being forced to be uncorrelated with each other. But we can sort of say we already have a better solution. Here's a non-orthogonal solution. So this is a rotated oblique. Non-orthogonal means generally you'll see the term oblique used. I've just now, although I want to say these are not my slides. I want to give credit to the person who produced these lovely slides to explain rotation, because I was very happy to have found these. So here the same dots, the dots still haven't moved, right? You can see in all of these that the dots haven't moved. All we're doing is moving the factor axes around, and now we're allowing those factor axes to move closer to each other or farther away from each other in the other dimension. And generally this will produce a more interpretable solution. And in fact, if you're trying to reach what we talked about before and called simple structure, if you're trying to reach simple structure, the oblique solution is generally the best fit. And here's another visualization of that. So we talked about simple structure as being that structure in the factor item association matrix. So think about it again. Let's say we are extracting two factors. There's going to be two columns. Each item is going to have a value in that matrix that represents its association with the factor. And you want to maximize the association of each item with the factor it goes with or goes on to or belongs to, and minimize the association of that item with the factor it doesn't belong to. And that's, again, what we call simple structure. Simple structure does have some more strict criteria, but that's the plain language explanation. Sometimes that's called a Thurstonian rotation, right? Rotating until we achieve simple structure, because Thurstone was the one who pioneered this idea. And you will see that it's almost always more interpretable. You want your final factor solution, again, to rest on your decisions about interpretability, but generally this oblique rotated solution will be your preferred solution, and it will be that one which maximizes simple structure. So this is a nice representation of what simple structure is, and I'm not going to say any more about it because you can return to the slide. I will show you this though, because SPSS does not make this easy. R does make it easy to really explicitly tell the machinery which kind of rotation you want in SPSS. Again, because SPSS has been around forever and the terminology has just been brought forward. So in SPSS, the rotation methods that are available to you are things called Varimax, Quartermax, Equimax, Oblement, Promax. And so I just wanted to put this up here so that you could remember, have a reference to return to if you're using SPSS about which of those options are the oblique options. Okay. So now we've gone through all of those steps. We've performed the exploratory factor analysis. We've chosen the extraction method, which is the principal axis factoring approach, which is synonymous with a true exploratory factor analysis. We've looked at the communalities. We've used the communalities and the eigenvalues in the scree plot to decide on the number of factors that we're going to retain in the model. Then we rotated. So both of those, the rotation has to happen after the decision is made about factor retention. And now we're going to try to interpret the results of the factor model. So this is also a little complex, and this is an SPSS specific slide or an SPSS specific problem. We want to look at results that represent the item factor structure of our rotated solution. So something comes out of the results that's called the structure matrix. That's not what we want. Something may or may not come out of your results called the rotated factor matrix, which also sounds like what we want. It's not what you want. You want what's called, if you're using an oblique rotation, you want the SPSS result called the pattern matrix. If you didn't rotate, you won't get a pattern matrix, in which case you would then want the structure matrix. That's just an SPSS historical hanger-oner. Okay, so we said we were going to look at the pattern matrix for our non-orthogonal rotation, and we're going to interpret each entry in that pattern matrix as the correlation of the item with the factor. Let's just say that again. We're going to look at the pattern matrix in our results, and we're going to interpret the values in the pattern matrix as the correlation of the individual item, the item level correlation with with all the factors. So you'll see in a second, because this is a non-orthogonal solution, and therefore we're allowing the factors to be correlated with each other, we've attempted in our extraction and the techniques that we used subsequently, i.e. the rotation, what we're attempting to do is maximize the correlation of an individual item with a single factor and minimize the correlation of that item with the other factor or factors in the factor model. But minimized doesn't mean eliminated. I hope it makes sense if you're allowing the factors to be correlated, that each separate item will still be correlated with every factor, just to a lesser extent with one factor than another. That's the simple structure that we're seeking. Okay, so hopefully that all makes sense. But now we're going to do some interpretation. I think I'm going backwards. Sorry about that. Oh, here we are. So we're going to look at and interpret the results from the pattern matrix. But they're not correlation coefficients. They are regression coefficients. So they're the relationship of that item with the factor to which it belongs or most hangs with, but partialing out the effects of the other individual items in the factor model. So to reiterate, the pattern matrix contains the unique contribution of each variable, right, each individual question to each factor, controlling for the other questions. And that is what we want. We don't want the full correlation because not all of the variance in each individual item was used with that single factor, right? So what we want to see is the contribution of that item's variability to the total factor variability, and that's what we're going to get. Okay, so take a look again at the questions that you saw in the exercise. In the exercise, you were asked to group these questions into buckets or piles that make conceptual sense. I can't remember if I asked in this particular recording for your piles to be named, but if we did this actually just conceptually with no analytic machinery behind it, we would ask you to have named the piles that you came up with. So generally, as I said, people will produce 2 or 3 piles here, where one is pretty clearly about the competence of the medical team or the health system, right? There's something has been missed by my doctors. The doctors don't give me enough information about my tests. Maybe you called that quality, but it's something about the system. And then there's the person's confidence. I'll use the word confidence because it does appear here somewhere, right? But it's also represented by the questions like, I know how to put my mind at ease. I have the knowledge and ability to treat the symptoms. I like to call this efficacy. And then often people will come up with something, there's an emotional component here, right? There's some distress or fear. So probably there's 3 things happening here, right? 3 buckets of individual questions. And what we want to know is, what did the exploratory factor analysis come up with? Here are my buckets. Here are my actual piles, right? This is my conceptual sorting. And if I had to name these, right, maybe I would call one of them emotional or socio-emotional component. That's the first one. That middle one is sort of the efficacy one. And the one on the far right is about the medical treatment or my confidence in the team or the system. Yours might have been the same. They might not have been. They might have been close. You might have called them something different. But in general, as I said, I've done this exercise lots of times. People generally tend to come up with about 3 things, and they more or less look like this. So here's the pattern matrix. I want to make a note here. So this is the pattern matrix for our non-orthogonal rotated solution. If you look, this is from SPSS. If you look down at the bottom, you can see this is principal axis factoring, i.e. this is a true factor analysis using a common factor model or modeling only the common or shared variance, and that it was rotated with an Obleman rotation, which means a non-orthogonal rotation. Again, those numbers represent the partial with a squared multiple correlation of that item with each factor. So look at the first item. I'm not sure if my symptoms are a sign of a serious health problem. That specific question or item is most highly related with factor 1. With factor 2, though, it still has a correlation, an R squared of 0.16, and with factor 3, it still has an R squared of close to 0.16. So what we're trying to do here, right, is get what we were calling simple structure, which is maximizing the correlation of each question with only one factor and minimizing the correlation of that question with the other factors. And if you look down the column, so for example, the first factor is factor 1. It has high correlations in the first group, 0.7, 0.6, 0.55, 0.52, 0.46, 0.42, right? So those are a version of simple structure that says in the column at the factor level, you should have high correlations of each question with only one factor. And that's our best solution. We want these, if there really are sort of three underlying dimensions here, then each item should be maximally correlated with only one factor and minimally correlated with the other factors. I'm going to break this out so we can see it more clearly. So all I've done is take that slide before, the long one, this one, and break it into three parts. So we can examine these correlations a little better. But in fact, this might be easier. So it looks to me that there are three factors here. That's what my scree plot told me. That's what the eigenvalues suggested to me. Looking at the pattern matrix suggests to me that I've achieved something close to simple structure, right? Let's look at factor 2. So factor 2, that second column, begins with question 10. I often don't feel like my doctors give me enough information about my tests. Question 8, I trust my medical team. If you look at each of those questions that have negative coefficients in front of the value in the factor 2 column, the R means that the question was worded in such a way, I trust my medical team, but that when it was scored, it was reversed. So that it should be interpreted as I don't trust my medical team. That's why the correlations there are negative, even though what is represented is the association of that question with that factor. You'll see that all of those coefficients are negative, right? So the negatives don't mean anything good or bad. What they say, as long as that group that's hanging together as factor 2, which is the group that begins with negative 0.7, negative 0.7, negative 0.6, negative 0.56, negative 0.54, that's your second factor. And it makes sense conceptually as a factor because it's about trust in the system. I don't trust my medical team. I'm unsure the doctors have adequate knowledge. I don't think my symptoms will be taken seriously, and I'm not sure whether the treatments are going to improve my symptoms. Those all go together in a group. That's this factor 2. And then factor 3, what always happens in an exploratory factor analysis is the last factor is like straggling in, right? He's always the factor with the lowest eigenvalue. That's just how the method works. And the correlations generally are lower of those items with their own factors. So look down the column for factor 3, but we've still managed to achieve almost something close to simple structure in that looking down the column, the correlations of the questions with the other factors are minimal. And looking at the row level, the correlations of each question with that factor are high. What I've done in SPSS is chosen a couple of options that suppress small coefficients. So the empty boxes are coefficients that are less than 0.15. That's just an option that you can find and click. It makes interpreting the output a little easier. The only problematic one here, well, a few problematic ones. So the very last question, question 9, and again, the ordering of the questions is arbitrary because I forced the output to show the questions in an order that corresponds to their correlations with each factor. So these questions are no longer in order. They're now sort of in factor order. And so if you look all the way down at the bottom, question 9, I don't know if my symptoms will interfere with my relationships at home and work. That has a correlation of 0.39 with factor 3. That's a good, but it also has a correlation close to 0.3 with factor 2. Not so great. That's sort of a problematic question. And if we were at the measure development stage and we were in a position to potentially revise the measure itself, maybe that might be a clue for us that that's not a very good question. The other problematic one might be question 7, which has a correlation of 0.55 with factor 2, but it also has a correlation close to 0.3 with factor 1. Question 15 up there at the top is also problematic. I think there's something causing my symptoms that has been missed by my doctors. That wants to go with factor 1, right? 0.59 is a high, R squared, but it also kind of wants to go with factor 2, which makes sense because we're thinking of factor 2 now as a factor interpretable as trust or confidence in the system or the physicians or the health system or something. So hopefully this like in-depth examination of the pattern matrix makes sense to you in terms of thinking about the underlying dimensionality or structure of this phenomenon. This is a phenomenon, a latent variable that has three underlying components, right, or dimensions to it. The question of whether or not those are separate phenomenon or not separate phenomenon or should be modeled as three separate individual factors, which have nothing to do with each other versus three sort of sub factors of a larger thing, is a question that you would answer using a confirmatory factor analytic approach. Remember, exploratory factor analysis is not an inferential technique. It's a subjective technique driven by a lot of decisions on the part of the analyst. I didn't present here the unrotated matrix, but it might look quite different. And in fact, it does, and it makes interpretation much more difficult. If we were using this at the measure development stage, we might use this information to revise the measure by removing some items, rewording some items, which would necessitate then going out and re-administering in a new sample, taking a look at it again, which is always a lovely thing to do. Nonetheless, I hope this example is useful and helpful because for me, I've always been astounded by exploratory factor analysis. Like, I looked at the items myself, right? I did in my head a conceptual examination, maybe, which ones might hang together. And then the machinery of EFA produces numerically or analytically the same result. It's just an astounding thing. It's, again, an act of discovery, as Joel Michel would say. This is just, as I said, the same pattern matrix, but broken down. So I don't think we need to look at that. Here is some technical details about the elements of the matrices that factor analysis will give you. We're not going to look too much at that, except unless you need to come back to it someday to answer some technical question. Okay, a few closing notes. There are other extraction techniques. We have used a principal axis factoring approach, which isn't necessarily the same term that would be used in a different piece of software, but it is the one that's used in SPSS. And we've contrasted that with a principal components analysis because that's another approach to extraction. But there are several others available in SPSS. And if you're using an R package, for example, there are more still available, some of which might be maximum likelihood based. The ones that we've looked at here are OLS based, right? Ordinary least squares regression based modeling, not maximum likelihood, which is a different approach. Every approach, though, is capable of producing a score. Each individual in your sample will have a score on every factor, indicating the extent to which they possess, or the quantity of which they possess of that factor, of every factor. We're not forcing orthogonality because that's generally an unreasonable approach when coming in with your own sort of common cause factor model. As I said, this is not an inferential technique. There are no answers here. This is an exploratory and descriptive technique. There are no p-values. You saw that hopefully going through all of these slides. There are no p-values. You are making, the analyst is making the final decision about what's what. It's a correlational technique, so it's sensitive to sample size and sensitive to outliers. And in terms of the subjectivity, again, there's no real question or no real answer to the question, is this factor analysis good, right? There's no answer to that question. The answer to that question comes from the confirmatory factor analysis, which is in a different presentation. But if you have a large enough sample, you can certainly split the sample randomly in half and run the EFA twice for sort of cross-validation. What's more common in a large sample is the exploratory factor analysis is followed by the confirmatory factor analysis in the other split half. And you can look at the reproduced correlation matrix because remember, we started off by saying mathematically what's happening behind the scenes is the model is attempting to reproduce to the extent possible the original correlation matrix. So you can look at the correlation you can look at the reproduced correlation matrix, the correlation matrix that's implied by the factor model. And you want to see a small number of correlations that are, not close to the original. In the confirmatory factor modeling, this is a much more specific approach to asking the question of model fit, which is, to what extent did my factor model reproduce the original pattern of the variance covariances or the correlations between the items? And one last time, so I'll close this by saying, right, EFA is a complex multi-step process with few absolute guidelines and many options. That's from the Costello and Osborne paper, which is just a fancy way of saying that it's a subjective technique and almost always should be followed by a confirmatory analysis, which is the topic of the other slides, a confirmatory factor analysis. It's rare nowadays to see exploratory factor analyses conducted by themselves. So if your plan is to look at dimensionality and structure of an underlying set of questions or items assumed to be coming from the same data generating source, then you absolutely must have a large enough sample to split it in half, do an exploratory model first and a confirmatory model second. So the last couple of slides are just the way to conduct these in SPSS and R. So I'm going to sign off with that and say thank you very much for your attention, and I hope that this was helpful to you.